Well, guys, welcome to our Tuesday lecture. If you can, I truly appreciate it if you turn your cameras on, as you would see that it's so constraining and so boring to speak into the void. When I see your faces, I feel like I'm talking to somebody. So may I, before we begin, answer any of your perennial questions? Do you have any? One obvious question, do I curve? Do I curve, guys? What do you think?
Nope.
Well, that depends what you mean. I mean, we do study curves, right? So curves are can be simulated by a polynomial interpolation. So in that sense, I curve. Understood? I once curved a picture of a hippopotamus by just writing a few points along the hippopotamus and interpolating it with a polynomial. Okay? Polynomials are very versatile. But the idea of curve is a very strange idea, guys, which I hope you understand. Right? Either you know something or not. Right? It's just like, it's not like we're not competing on who constructed the worst, the least terrible bridge. So I'm hoping that you understand this material, and we are going to insist upon understanding. So with that said, I would say that on average, at least from what I heard, around 50% fail the class. With me, it's less. So I do everything I can to give you points here, point there, and I don't grade too heavily, but at least maybe that's my impression. Maybe it's a wrong impression. What you should do is prepare. That means you should be solving problems all the time before, not because they're assigned, but just because you need to understand the subject. Good? Now let's consider what we talked about last times, guys. So would you remind me, do you remember we spoke about a stunt double? Now, what is a stunt double? Is it a strange question? Similar equation. Jeffrey, I think you get the idea, right? And you just kind of use this wording, but also always try to have the right wording. Guys, you all watched a movie. Now, you have an expensive prima donna actor who does not or cannot risk his life and limb for the movie. And what do you do? In other words, he is not easy to work with. So what you have is somebody expendable that you can throw off a roof, that you can beat up, that you can shoot at. That's a stunt double. Somebody that's very convenient to work with. And that's called cascadeur, as anybody who wants extra credit points knows. Right? It's a word in Russian, it's a word in French, it's a word in German. Probably comes from French. Okay, guys, and a stunt double, we gave this example. Do you remember? Suppose we were interested in approximating, say, 4.01. Now tell me, without a calculator, what would you have done? And you don't have to kind of follow calculus. I'm just asking you person to person. So you are asked, what is root of 4.01? What answer do you throw? So Elazar, thank you. You say just a number 2 and maybe a number slightly bigger than 2. Wonderful. Right? Now you could do a little bit better. Okay, John, thank you so much. Thank you all of you, around 2. Good. You can do a little bit better. And for that, let's for a second go back to the regular screen and consider this function, right? We're definitely dealing with a square root function. Now, why would it not be immediate? Square root function, we know how we can calculate root of 4, not calculate, we just guess it, right? Root of 4, root of 16, several roots we can calculate. Now, do you observe that if I look at the number 4, here is the number 4, I try to place it in the middle. Do you see that I see here on the x-axis, I see a lot of numbers. Now I can begin zooming in. Do you see what's happening, guys? So as I zoom in, fewer numbers are visible to me. You see where is 4.1? I said 4.01, right? You see what happens? As I zoom in, the curve looks like a line. The value at 4 is exactly 2. And the value near 4, let's say this is 4.01, is somewhere over here. You can see where it is on the y-axis. You see the y-axis values? You see the point? Now, that means that within some vicinity of 4, this is the vicinity of 4, the curve looks like a straight line. You clearly see why it is the derivative. Yes, guys, why it's the tangent line? Because when you zoom in, your horizon on the x-axis shrinks, right? It's closer and closer to 4. I keep 4 in the center, so I see fewer and fewer points on the x-axis. Yes? Which means that the point 4, 2, and the second point that I need to calculate the line, that I need to calculate the slope, they're very close together. So that means that what I zoom in at must be the tangent line. And I use that to calculate. You understand what it means? That means that the tangent line is using very basic formulas. It's a very basic polynomial, the easiest polynomial to use because it's degree 1 polynomial. That's the idea, right? You can use degree 2 polynomial if you want a better cascadeur, which is what you do to approximate, perhaps. That's the idea of infinite series. Good. So what do? We consider this function. We consider the graph of root of x equal to y. And this is that graph. And we look in the vicinity of 4. And in the vicinity of 4, I can draw a tangent line. And that tangent line, if I select an interval, short interval around 4, that red line is not going to be, in my drawing, it looks like it's very different, but in fact, it would be very close to the actual, to be very close to the actual curve, right? So what is 4.1? 4.01, it's somewhere here. It's somewhere over here that I want to calculate on the complicated function. But instead, I will calculate it on the cascadeur function, on the stunt double function, or what you call it in the book, it's called linear approximation. You understand why it's called linear approximation? Because you look at the graph and you approximate a non-linear graph by a line. So what you see is that the tangent line here, this red line, has what equation? The cascadeur function has the equation y of x equal to root of 4 plus 1 over 2 root 4 x minus 4. Everybody understands what I did here, guys. We did it many times in class. I just found the equation of the tangent line and I converted it to the y-intercept form. Now, what's the benefit? Look at it. So instead of calculating root of 4.01, I see that it's very similar to root of 4 plus 1 over 2 root 4, 4.01 minus 4, which I can easily calculate because root of 4, it's 2, plus 1 over 4, 4.01 minus 4. Notice that here I do not have any way to calculate, whereas here I carry out the calculation very rapidly. Now, guys, the purpose of this is not at all to approximate. It's a very, very bad procedure to carry out numerical approximations. What is the purpose is to analyze the behavior of the function at a microscopic level. To decide what are the transistors, so to speak, what are the organelles of that function doing, if you prefer biological simulation. And this idea becomes more important as you study more complicated mathematics. So if you were to go and study complex analysis, it is incredibly complicated. But it's not the reason it's called complex analysis, or maybe it is, but you understand the graphs are two-dimensional shapes suspended in four-dimensional space. They're extremely difficult to visualize. And it's extremely difficult to understand what complex functions do. But with the derivative, if you get an interpretation, it's the stand double that's going to help. And that's what we're actually going to see today, how the stand double can help. You ready? So here is the idea of a stand double, guys. So if I want to find, for instance, here is a very easy example. Find expression for f plus g prime in terms of f prime plus g prime. Okay, now you know that, sorry, in terms of f prime, it's equal to it, in terms of f prime g prime. Now, clearly you know that formula. You know that the sum of the derivatives is the same as the derivative of the sum. Right? This is not a very interesting formula. I'm just showing you how that idea works. This stand double idea works to also establish this formula. We're going to apply it to something much more complicated. Ready? So this is what I do, guys. Look at it. F of x is essentially equal to, near the point A, essentially equal to f of a plus f prime a x minus a. That's the form of the tangent line. This is the stand double form. This is what the curve looks like if I zoom in at the point A. Yes? Clear, guys? Now, because x minus a is very short, I will write this as simply f of a plus f prime a dx. This dx just means there is a very small distance, that's why little d, between any x that I can see on my horizon and the point A at which I zoom in on the x-axis. Clear? So dx is this expression of the quantity being the horizon getting shrunk. That's the stand double. Now, the stand double for g of x at the same point A is ga plus g prime a x minus a, which I can write as ga plus g prime a dx. Now, the question is, what will I see if I zoom in on the curve f plus g? What will I see? Well, if I take f of x plus g of x, again, why do I mention stand double, guys? This is the interaction between f and g, but f and g are prima donnas. What do? Instead of calculating the interaction between f and g, the stand doubles will simulate that interaction. Do you understand? That's why I call it stand double. So what is that going to be, guys? This is simply going to be the stand double plus the stand double of g. Which is what? Which is simply, I can add the constants. So this is f of a plus g of a, plus I can factor out the dx, and I have f prime a plus g prime a dx. Do you see what it is, guys? Here is the y-intercept and here is the slope. We just recovered something very obvious. We recovered that the derivative of a sum is the sum of the derivatives, because what is it geometrically? It just zoom in and report the slope. Zoom in, see a line, report its slope. The slope you're reporting is the derivative. Are you clear? Very easy. Correct, guys? Now, this formula, I mean, you did it by definition. We can now try to figure out using the stand double idea, and that's what I want you to do, guys. What will you do? And we have the same setup. How would you find out the derivative of a product at the point A? Okay. I want to know the derivative of f of x times g of x. So find f x times gx prime at the point x equal to A in terms of f g f prime g prime. You understand? We're trying to come up with a formula for the derivative of a product. What are we trying to do? We are zooming in on the function f times g, and we are hoping to see a line, but we don't see anything because, I mean, but it's abstract here, guys, right? So I am hoping to understand formally what is the line that I will be seeing. Are you clear? So help me do that. So if I multiply f and g, guys, that the idea is very simple. What should I multiply? Guys, I think you suffered from not having watched movies recently, I'm sure, right? You don't watch any movies, right? You don't remember what a stand double is, or you don't know how movies are made. If I take f multiplied by g, what do I deal with? Yeah, Safa, I mean, it's not, we don't care if the formula is, if you know the formula or memorize. My point is, can you construct the formula on your own? And that's because there are more formulas that you construct on your own that can fit in any textbook. All right, what is mathematics is ideas and being able to communicate ideas. It's several things: clearly thinking and being able to communicate what you think clearly. Now, if I multiply and the actor f times the actor g, what instead may I try to multiply? Yes, Aaron, correct. I multiply the stand doubles, the linear approximations. Very simple, guys. Isn't it tremendously simple? If you are having two actors that are difficult to work with, you replace them by their stand doubles. Do you follow? So if I have to multiply f of x times g of x, again, guys, I hope you understand the idea, right? It completely doesn't matter to me if you memorized the derivative formula. It completely is not what this class is about. Right? I mean, you can memorize something. I'm hoping that you just your mind is elevated over something, right? You're not sunk in this swamp. So f of x times g of x is approximately what? It's approximately f of a plus f prime a dx multiplied by ga plus g prime a dx. You understand why I do that, guys? Because I know the linear approximation form of each of them separately. And I say, okay, to calculate f of x times g of x, where x is in the vicinity of point A, I might as well use the simpler equations, the linear equations. Now let's try to understand what happens if I multiply it, guys. Okay, can you multiply it, right? I'm going to group it by number of times dx is used. So no dx, dx to the power of 1, dx to the power of 2. Dx is just x minus a, where x is very close to a naturally, because that's only the condition when we zoom in. So look what happens. This is f of a times g of a. Here we have no dx. Now where do we have dx? We have dx here and here, right? So so to multiply, let's say multiply 1 dx times no dx and 1 dx times no dx. So if you combine it, guys, it's just foiling. If you combine that, this gets you to f prime a ga plus f a g prime a dx. Are you following? And then there is one term that has dx squared. You understand what I did, guys? I just foiled it up and I grouped based on dx to the power of 0, dx to the power of 1, dx to the power 2 is what's missing. There is only one way to get dx to the power of 2 if I take and multiply both terms that have a dx next to it. So this would be plus f prime a g prime a dx squared. Now tell me, okay, I have this. So how is it useful to me? What am I going to do now? Any ideas? What is this expression supposed to tell me? Well, let me help you then. Guys, do you understand what this dx is symbolizing? This dx is the horizon, right? So you imagine you zooming in at the point A, and dx is a sort of how far can you see on the screen, right? How much is that zoom in? Okay, so dx is a very small number, because if you have a very, very big zoom in, it eliminates a lot of the numbers that are farther from A, as you saw when I was doing zoom in for root of x, correct? So this dx can be, under very powerful zoom in, can be made 1 millionth of 1 meter. That means 1 micrometer. If you like biology, you all know what's 1 micrometer. It's a scale that there are many bacteria that are 30 micrometers long. 1 micrometer is tiny, correct? So if dx is 1 micrometer, what is dx squared? You understand? Dx, I zoom in. It's basically, it's the idea of selecting closer and closer, making the interval, the x-axis centered around the point A, thinner and thinner, that interval. So I can imagine that dx, under more and more zoom, I see only what? Only 1 micrometer. Okay, that's the only thing I see. And if I multiply it, you see, I zoomed in 1,000,000 times. Whatever was 1 micrometer in length will now be the length of 1 meter. Do you understand? 1 micrometer, 1 millionth of a meter. If I zoom in at 1 micrometer 1,000,000 times, it will look to me like it's 1 meter long. If I have a screen that's 1 meter long, 1 meter wide, better said, right? Then micrometer is everything I see on a 1 meter screen. It's a very wide screen. You agree, guys? It's like a big TV that you have. Like you see, my hands, I cannot, they are reaching. So this is somewhere over here is a meter. I cannot even show you, right? So if in that big screen, you only see 1 micrometer, will you be able to see dx squared? That's my question, because dx squared is how much, guys? If dx is 1 millionth of a meter, how much is dx squared? Dx squared, same. Dx squared is dx multiplied by dx. 1 millionth of a meter multiplied by 1 millionth. Is it the same as 1 millionth? 1 squared is 1, but dx, so dx is what? So it's 1/1,000,000th of a micrometer. Do you understand? So if dx is the size, if what you see in dx is 1/1,000,000th of a meter, then dx squared will be 1/1,000,000th of that, which means that if you enlarge and make dx 1 meter long, dx squared will look to you like a micrometer. You follow what I mean? So dx will not be visible, and the smaller you make dx, the less visible in relation is dx squared. Dx squared will be so basically make dx 1/1000,000th of a meter. Then dx squared is 1/1000,000th of 1/1000,000th. You understand? Dx squared disappears much more rapidly than dx, which means, if you understood what I'm saying, guys, I hope you do, which means that because in this formula, I'm just zooming in, perpetually zooming in at the point A. Do you understand? It's an animation. You're zooming in, and you never stop. And on the x-axis, you just keep the point A centered, and you can see, the points that you can see the integers eventually vanish. You just see A and no other integer, right? And then the decimals eventually vanish, and the 100th powers, 1/100, so vanish. And all you see eventually is just things that are extremely like A, to correct to billions of decimals, and then correct to trillions decimals. As you are zooming in, as you continue zooming in perpetually, dx squared will disappear. You understand? You will not notice dx squared. You cannot see it anymore. Clear? So that means what, guys? So that means that since you are multiplying by f prime g prime, they just scalar multiple of dx, which means this formula here is your linear approximation. That's the line that you will be seeing. That is why when you zoom in, you see a line. Are you with me? It gives you the building block. That's why you see a line. Here is the equation of a line. That's the y-intercept, and here is the slope of that line. Do you see what it is? That means that the slope of the line, this is what we just established, guys. We established that if you take f of x times g of x, and we take the derivative at x equal to a, that will be f prime a g a plus f a g prime a. Are you with me? So confirm that you are or you are not, guys. I mean, I'm hoping to reach through you, right? You might think I'm teaching you calculus, but I'm trying to start your visual cortex and other cortexes that you possibly, hopefully, still have. That's great, with me. Guys, you have to think of scale. You have to think of so many things. That's the only, if it's when it's hard, that means that you are pushing beyond your current limits. Okay, and that's what you hopefully can do. Push beyond your limits, that's how you become bigger. So, this is what we have arrived at. So for instance, if I want to take the derivative of x squared times e to the x, guys, I see that it's a product of two functions. Each of them separately, I know to differentiate, correct? Each of them separately, I know how to take the derivative. So derivative of x squared, I know it's 2x, and the derivative of e to the x remains e to the x. So what I'm told to do by this formula that I just established, I just take the derivative of first function, multiply by the second without touching it, plus the derivative moves to the second function. Do you see the derivative travels? The prime moves from first to the next function, and there's addition in between. So what I have is 2x e to the x plus x squared e to the x. Good? Now I'll give you one more question like this just to see that you understand how that works. So tell me, first of all, what is the derivative of x to the power of 1/7, please? You can be fast. I mean, I'm just interested in what's the result. I don't really care how you get to it at the moment. Okay, so I have now 2 people responding. To which power, guys? So x to the 1/7, right? So what happens is the power rule works this way. You drop this 1/7 and you have x to the 1/7 minus 1. I mean, maybe you feel that we haven't proved it in class. You're right. We only proved the power rule for positive integers, but it's true for all constant powers. Good? So that would be minus 6/7, right? So the answer is 1/7 x to the power of minus 6/7. In general, guys, only because I'm not sure if you appreciate it, the derivative of x to any alpha is alpha x to the alpha minus 1. This, of course, needs to be established. I hope you do remember the proof for the power rule when the power is a positive integer. You can expand it to other situations, which it's not always very difficult. It's a bit difficult, of course, for the situation x to the root of 2, because I don't even necessarily understand what it means to take root 2 as the power of x. Correct, guys? What's the operation? On the other hand, e to the power of root 2, presuming I understand what root 2 is, I understand that very well. This simply means 1 plus root 2 plus 1/2 root 2 squared plus 1/6 root 2 cubed, and so on. I hope you remember that. Yes, guys? That's what we established is e to the x. We established it to some extent. I mean, if you are interested deeper, you of course can establish deeper. Good? So now we understand what is the derivative of x to the power of 1/7. Now tell me, please, what is quickly the derivative of x to the power of 1/7 times, well, times, let's say, e to the x. I will give you more interesting examples once I have those examples. We just have very few functions. We only have exponential functions. We only truly know how to differentiate e to the x at the moment, and polynomials. All right, let's see what we have here. Why just 4? You're reversed? Where are you reversed? Are you anywhere? Who is reversed? I see you do it, but I see you. I prefer to think of the traveling derivative. Okay, so that, guys, should take you. This is not an. This is just to confirm that you understood how this rule is working, which of course you confirm by proving it. Right. So what is this? This is first function, second function. So we have derivative of first times second, which is 1/7 x to the minus 6/7 times e to the x plus, don't bother the first function, multiplied by the derivative of the second. So that would be, it just happens the derivative of e to the x is e to the x. Good. Now that was very boring. Now I think you are ready for a challenge, correct? You want to now figure out the quotient rule. We just figured out the product rule. Now let's see if you could, using the geometry, figure out quotient rule. Why, Elazar? Why not? Just think about it. So I want you to tell me what's f divided by g prime. Figure out the formula. It doesn't matter to me if you remember this formula, right? That's completely beside the point. I am hoping to teach you to think using calculus. Not for this formula, you can find it online. For many, many formulas which you will not be searching, you would need to use it. It's like you know. Yes, remembering this formula, that's besides the point. Establish it. All right, I will return in 4 minutes, since it should take you at least that long, yes? Don't be bored. Interesting, Dauda. We shall see, of course. Elazar, interesting idea, but what's the derivative of 1/g? I want you to see, there are several things. I mean, you can derive it in many ways, but one thing I'm interested, do you understand the stand double idea, guys? Right? No, why is it g to the minus 1/2? Elazar, incorrect. No, that is not. Okay, let's do it together. Are you ready? So first of all, we can construct the derivative by zooming in at the point A. Do you agree? So what do we have here, guys? So we zoom at point A. We consider the quotient. Let's just, it's a bit big. Let me just write it here. We consider the quotient fx over gx, which is approximately what? If we divide f by g, guys, we do what? Instead of dividing f by g, we do what? Subtract. Guys, you definitely haven't worked in the cinema, haven't you? If you are going to make, you see, I'm here, guys, but I hope you understand I'm going on autopilot for most of the time, right? So my brain is, oh, it's somewhere else, right? I just speak, but my soul is flying somewhere else. So if my soul is doing, right? What is my body doing? My robot self is doing. It's also doing, right? So if I take F and divide by G, what are the stunt doubles doing? Yes, I am the stunt, exactly, right? My body here, it's an imitation of Arkady. Arkady is not here. You might have not noticed, but Arkady is not here. Hasn't been here for a long time. Exactly. He is dead. Well, not always. Sometimes he's not in the tower. He is also in the dungeon. Yes, he was a pilot. He used to fly. But now he lost his wings. So that means dividing. So we have what? We have f of a plus f prime a dx. The king of the Neanderthals, apparently, okay. Who is the king of the Neanderthals? Divided by g of a plus g prime a dx. Yes? Now, guys, can you continue from this point? Do you see what I did, guys? Instead of dividing f and g, that's a very simple idea. What I'm saying is, the idea is take the stand doubles and work with them instead of working with the prima donna functions. And by the way, some of you disappeared, right? Why do you disappear, guys? Why do you leave me? Why do you forsake me? What do you do next, guys? Your favorite thing? Well, I believe that, Elazar. Multiply by the reciprocal. Exactly. You multiply by the reciprocal. Now look what happens. So what we have, if we multiply by the reciprocal, by the conjugate or reciprocal of the denominator, I will get GA squared minus G prime A dx squared. And what do I get in the numerator? In the numerator, I simply write f of a plus f prime a dx multiplied by g of a minus g prime a dx. You understood? I multiplied top and bottom by ga minus g prime a dx. It's not an easy, this is one of the harder formulas to figure out this way. You just have to have a sort of feel for what's happening here. So when you multiply it out, what happens? You have f of a times g of a in the numerator. All right. And then what do we have here? Then we have how many dx terms? We have this term multiplied by that minus this term multiplied by that. So that will be, when I factor it out, it would be f prime a times ga minus f a g prime a dx, and there is still the dx squared term. You see this multiplied by that. So that would be minus f prime a g prime a dx squared divided by ga squared minus g prime a squared dx squared. Are you with me, guys? It's a bit difficult. A bit difficult. I mean, you see, you should at least, you see, guys, you should at least see the idea, right? Stand doubles replace, you see that the idea is what I care about, right? What do I care if you see this formula somewhere else? It's not about the formula, it's about your thinking. So, are you with me? Right, yes, right, no. Maybe if I should explain something. Following Jeffrey, good. And the others? Good. With me? Okay, Sarah, that's good. Yes, you don't feel any pressure, guys. You know, I'm not sure what I cause you to feel. As I mentioned, right, I am in many ways on autopilot. So the expression is I can be angry, I can be smiling. I'm a stunt double here. Very placid on the inside. So if we're here, then tell me which of those terms they become unimportant, right? Because the idea is we are zooming in on this curve and we want to know what sort of line we will see. Now, if I zoom in, where dx is a very, very small number, then the dx squares are going to be invisible. Do you understand, guys? You might be confused. Well, dx is a small number, so I cannot see dx. Why would I? What does it matter if I can see, if I cannot see dx or if I cannot see dx squared? So what you do when you zoom in, you make dx, you make that your full screen. You understand? Dx is your full screen when you're zooming in. Are you with me? And dx squared is just by comparison very small. So if you zoom in a lot, the dx squared is going to be a proportionally tiny number, which means it is invisible. This is essentially the same thing as f of a g a plus f prime a g a minus f a g prime a dx divided by ga squared. Yes? And if I separate it, look, guys, what it looks like. If I distribute the ga squared, I get f of a divided by ga plus this formula, f prime a ga minus f a g prime a divided by ga squared times dx. This is my derivative formula. You see, this is the intercept and this is the slope. I got my derivative formula. All right, so first, guys, let's see what sort of sense do you have? If I have a derivative of two functions, we have this traveling derivative formula, yes? Derivative of two functions, we have, it's a f times g prime. That would be simply first function, second intact, plus first intact, second derivative, yes? The derivative moves from f to g, from first to next. It's traveling derivative. Can you guess what will be the formula of triple product, f times g times k? What will that be? Thank you, Safa. Alessandra, thank you so much, and Jasprit and all of you. What about more people? Don't check out. No, it's not the chain rule. All right, so everyone who answered, they answered correctly. Yes, writing, Jomeo, thank you. You can easier to write to suppress the A, so it's shorter, but you are correct. Here is the situation, guys. So the formula is as you expect. Derivative of first function, then derivative of middle function, then derivative of last function. This follows easily if you establish the pairwise product rule, because the derivative of a triple product is like the derivative of the box times the second function. Yes? Now, by the pairwise product rule, that's the derivative of first of the box times the second plus the box derivative of second. So here, I just have to calculate derivative of f times g, which is this. And when I distribute, it is exactly as I expected. So we're good, right, guys? We understand the product rule. We understand, we can remember it, but we also can derive it. I did mention to you guys that you should be able to derive it using the definition as well, right? So you should be able to use any of those ideas. It's very good for you. It's not because you could look at many things, but again, we are not trying. I'm hoping you understand what we're trying to accomplish, right? We're either memorizing a phone book or we are actually learning to think. So the derivative, look at it, guys, derivatives of higher orders for product. Let's see if you can observe some interesting relationship here. So here is the derivative taken once. It's f prime g plus f g prime. Here is the derivative taken twice. So to take the derivative twice is to take the derivative again. So it's derivative of f prime g plus f g prime. And what happens here? For the first part, guys, look at it. This extra prime is with f, then it moves to g. And then first it's at the f, and then it moves to g. Do you see this? Here is motions for the terms f prime g. It's this prime is with f prime, then it's with g. Here it is. And then over here it's with f, and then it is with g. If I add it up, look what happens. It's double prime fg plus 2 f prime g prime plus fg double prime. Notice the primes add up to 2. Here we have 2 of them. Here we have 2 of them. Here we have 2 of them. Notice also this 2, and then we have 2 here, and then we have this term. Does it remind you of anything? Perfect square. Very good, Alessandra. It reminds you of perfect square. What about the next line? Let's try to see if I take 3 derivatives. Then I take the derivative of the second one more time. And when I simplify it, look what happens, guys. 3 derivatives of fg plus 3 double derivative of fg prime plus 3 f prime g double prime. This looks like the cubic expansion. Are you understanding what I'm saying, guys? It looks like what you're doing is like a binomial expansion, if you remember what it is. X plus y to the power 1, x plus y to the power 2, x plus y to the power 3, and so on. Here you can see the similarity. X plus y to the power of 1, it's x, y. Right? X plus y squared, it's x squared plus 2xy plus y squared. X plus y cubed, it's x cubed plus 3x squared, y plus 3xy squared plus y cubed. Yes, like using Pascal's triangle is a faster way to do it, Grant, precisely, which is where we are headed, of course, right? But it looks like the binomial expansion. You with me? Now, we can understand what happens symbolically. Symbolically, what we have is, we can imagine that this notation d sub f means take the derivative of f, and d sub g means just take the derivative of g. You understand? I create operators that work on individual functions f and individual function g. Now let's see what happens if I say df plus dg to the product. I can imagine distributing that to df and distributing that to dg. Look at it. And df of f times g, it doesn't touch g, it just takes derivatives of f. Whenever it sees f, it applies f prime. So you see it becomes f prime g plus f g prime. Yes? Now, if I were to apply df plus dg twice, it's the same as df plus dg squared. Means you see, because just the way the distribution works, it works just like with arithmetics. That's the type of thing you study in abstract algebra. So what you have is df squared, then it takes twice derivative of f, and then take another derivative of f. You understand? You apply primes. Every time you see an f, you apply prime to it. Then 2 times df dg plus dg squared. Right? And in general, the expansion for df plus dg to the n can be very quickly calculated using Pascal's triangle. Here is Pascal's triangle. So what you do is you write 1, then you write 1 and 1 on the sides. Those are the coefficients of the expansion to the power 1. Now, to obtain the expansion for power 2, just write 1, and then between those two ones, you put a 2, and you put 1 here. For the cube part, you write a 1, and then between 1 and 2, you say 1 plus 2 is 3. You write a 3 right below them, in between. 2 plus 1 is 3. And here you put 1. You can see we obtained this row. And now the next one, you just put 1, and then here you go 1 plus 3 is 4. Then 3 plus 3 is 6. Then 3 plus 1 is 4. And then you put 1. Those are the coefficients that expand to power 4. So what are those coefficients supposed to do? Here, if I expand x plus y to the power 4, it would be 1 times x to the 4. Next, I drop the power of x by 1 and give it to y. And that would be 4x cubed y plus 6 x squared y squared. Notice the powers always add up to 4. Okay. Next, it will be 4xy cubed, and finally 1y to the power of 4. Now, if you understood, guys, I would like you to tell me the coefficients in expanding to the power 5. What do I write as the line below? Please type it in the comments. Okay, yes, you missed 110 precisely. You have to have more tens. So here is how it goes. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1. What does it mean, guys? It means that if you take x plus y and raise it to the power 5, that would be x to the power 5 plus, you see this 5? 5x to the 4y plus 10x to the 3y squared plus 10x squared y cubed, and onwards. You understand, right? You understand how this expansion works, I hope. Okay, guys, so let's try to calculate the expansion of x to the 5 e to the x, taking the derivative of it 3 times. So I want to take x to the 5 e to the x, and I want to take 3 derivatives. And I want to be quick at it. Ready? So first, this is my function f, and this is my function g, and clearly I will need to know the derivatives of f. So f prime is 5x to the 4. F double prime is 20x cubed, and f triple prime is 60x squared. Exactly, Grant, right? So then I have the coefficients 1, 3, 3, 1. Yes? So what do I use those coefficients? So according to this formula, I have to calculate the expansion df plus dg cubed, which will be df cubed plus 3 df squared dg plus 3 df df to the power of 1 dg squared plus simply dg cubed. Okay, applied to this function. What does it mean? Triple derivative of f. So my solution is that x to the power of 5 e to the x triple derivative. That would be what? That would be triple derivative of f, which is 60x squared multiplied by e to the x by g not touched, plus 3 multiplied by double derivative times the function g prime, but g prime is just e to the x, so I'm not dealing with anything too hard, right? Derivatives, it's not reacting to it. But next is plus 3. I need one derivative of f, so I take this. Five x to the 4 and 2 derivatives of g, which is e to the x, plus only the derivatives of g. So it means I take the function x to the power 5, don't bother it, and take 3 derivatives of g, which is just e to the x. So very quickly, I was able to establish that formula. Let's see if you understand. Let's consider the situation, guys. So let's suppose we have this product. We have, well, we're really limited. That's unfortunate. So we have x to the power of 1/2 multiplied by x squared plus 2x plus 5. And I want you to take, this is, I mean, not very useful. I mean, I could have done it very fast, but I want you to take double derivative of that product. See if you can do it. Type in the comments when you're ready. Did I leave out the minus before? There was no minus. It was a product rule before. So good. So what do we need to do here? We have the function f and the function g. We can, of course, multiply it through and take the derivative this way, maybe faster, but why not do it this way? So first, I need to know the derivative of f, which is 1/2 x to the minus 1/2, right? And I need the derivative of double derivative f, sorry, which is minus 1/4 x to the, I subtract 1 from it, so it's minus 3/2, correct? In the power. And I don't need more derivatives. And I need the derivatives of g. I need g prime, which is 2x plus 2, and I need g double prime, which is derivative of that, which is simply 2. Good? So then the formula that I need to have is it's just df plus dg squared. So I will have to have df squared plus 2 df dg plus dg squared. Yes? So what happens here is what's the df squared? That's this function. So what I have, and this means don't take the derivative of g. So I first write minus 1/4 x to the minus 3/2 multiplied by x squared plus 2x plus 5 plus I take I take one derivative of f and one derivative of g. So it would be 2 times 1/2 x to the minus 1/2 multiplied by 2x plus 2. Yes? And then finally plus two derivatives of g, which is two derivatives of g is simply the original function x to the 1/2 multiplied by 2. And we're done. Good? All right. So here we learned a little bit about quotient rule. We derived it using a different process. We could have solved it differently, guys. I would have given you another problem. It's just we have no trigonometry at the moment. We have very few functions. I kept the other functions still away from you. We really know very few derivatives, and so those techniques will be more and more useful as we learn about different functions. Trigonometry is coming up soon, very soon. So the quotient rule works this way, guys. If I take f over g, you just square the denominator. That's what we found out. Don't worry, right? Before you can, before you can blink almost. So g squared is what is the square of the denominator. Copy the denominator, multiply by the derivative of the numerator, subtract the derivatives in other order. Yeah, I think before spring break. Of course, that's granted that I have no idea when spring break is. Right? I forgot what's spring, what's summer, what's night and day. You understand? Well, it's easy to remember that where the minus goes by just squaring the denominator and copying the denominator and multiplying by the derivative of f. Notice it's similar to the traveling derivative, but the minus is here. You see, so just take the number squared, copy it, and multiply by the derivative of the numerator, and then subtract, and the derivative and the non-derivative are reversed. And here is your task, guys. Calculate derivative of x to the 5 over 2 e to the x, please. So yeah, so okay, calculate it, guys. Just see a few calculations so far, just 2 over 3. Okay, Elazar. Okay. Aaron, the denominator, I think, squared and something else. I mean, I'm not. Here it is, guys. Are you ready? This is just a procedure. Just a procedure. So what is that procedure? Just the denominator we square, we copy the denominator and take the derivative of the numerator, subtract and reverse the roles. Okay, so denominator squared is 4e to the 2x. You see when I square it, and then the numerator becomes what? This is the denominator copied times the derivative of the numerator minus the roles reversed. It's just that 2e to the x, the derivative stays 2e to the x, and then the other function is not touched. Quickly calculate derivative of 1 over x to the 5. You can do it in several ways if you want to, but calculate it. Okay, that's good. All right, this one is easy, right, guys? Well, I mean, how many of you answer, guys? Some of you seem to be checked out. I have 1, 2, 3, 4 people answering it, maybe 6. There are what, 30 people at least here, 33 or 32. Why do I see so few? Simple, right? That's good. It's too simple for you to type. That's fine. If that's true, I am perfectly glad with such answers, right? With that bravado. Too simple to type, right? Don't want to exhaust your fingers. So here it is. We can solve it using quotient rule, even though that's rather different, right? So what we have is we can take the square of the denominator, copy the denominator, and sorry guys, right? I'm trying to read what you say. Yes, Elazar is admitting. I see. Elazar is just, you can just copy and paste from others, but not on the exam, Elazar. Yes, my dear, not on the exam. Because, you know, I had a dream about Peter the Great. tonight. You know what Peter the Great was known for? Well, for many things, for modernizing and for, of course, cutting beards, right? So hopefully that yes, that my dream will not come true. So what happens is we take the derivative of 1 over x to the 5, we square the denominator, we copy the denominator, and we take the derivative of 1 minus the roles reversed. So that gets to be minus 5x to the 4 over x to the 10. Of course, guys, you could have done something much simpler. I'm just using those ridiculous examples because we have few functions. So if you take x to the minus 5, that means the same thing. And if you take the derivative of that, it's minus 5x to the power of minus 6. Of course, you have to establish all those rules. But the point is, guys, you can do it much simpler. Understood? Wonderful. All right, guys, here is your next task. I am trying to be annoying. So take the derivative of this quotient. When is this class over? At 7:45? I don't remember. Or was it 8:50? You wish, Elazar. Do you believe in daylight saving time, guys? Right? Daylight saving time is really a nonsense. When I came here, I couldn't understand what it's for. Right? It's really 6:40 now, correct? I'm glad you agree, Elazar. So I think, yes, I think we stay here another hour, right? Just for you. All right, sorry guys to distract you. Go back to the derivative, just do it quickly. Yeah, it's too long, right? Annoying. We agree on it, guys. We don't like those questions at all, right? This is what you call practice question, right? So what do you do, guys? You see, there are several main operations, and here is if I had to do it, guys, if I really was forced to do it, what do? I first square the denominator. It's basically within quotient rule, I have product rule, agreed? So I square the denominator, I copy the denominator, and then I take the derivative of the numerator, which is will involve product rule, minus the derivative of the numerator, minus the derivative of the denominator and the original function. I ran out of space, so I put this box here, right? Here it is. And then when I carry it out, I get this expression. Don't need to simplify it because it's not interesting to us. It's only just, you see, guys, what do I want you to be able to do? Can you take the derivative procedurally? And if yes, then wonderful, you're good. Clear? Derivatives procedurally. Procedurally. And they say Russian is hard to pronounce. Breaks your tongue to speak in English. All right, guys, so that's product and quotient rule. And guess where we are at? Trigonometry is where we begin. So we have all those 4 lectures. By the end, yes, by the end, yes, yes. By the end of this segment, you can expect your exam, guys. So that depends how quickly we finish this, and of course, when I release the exam, I would like to see you practicing on the exam. Like, I don't see you asking me many questions, which means that you don't open the book outside of class. In the middle of April. Why middle of April? So so let's say this will take us how long? Depends how long it will take us to go through those 4 lectures. Good. Don't worry about the midterm, guys. You know what you should really be worried about? The final, right? I'm the nice guy here. The final, you see, I can threaten you, but I care, right? Usually you would be addressed politely with a smile. Cold cuts. Good. Final is going to be hard. Study. All right. I suppose you can go, guys, if you want to go. Take care. I'm not holding you. Goodbye.